One of the results of alpha particle scattering experiment is that a very small minority of the alpha particles are scattered through angles greater than 90 degrees. So what may be inferred about the structure of the atom from this result? So we know that an atom consists of a nucleus which is net positively charged, as it contains protons and neutrons are neutral while protons are positively charged. And if I throw some alpha particles on it which are also positively charged, the scattering is going to happen in sort of this way, where it is caused due to the electrostatic repulsion between the two particles, the nucleus and the alpha particles. Now, this exists in this system because alpha particles are again positively charged and the nucleus is also positively charged. So the greater this angle of scattering is, let's call it theta, that would imply that most of the mass of the nucleus or the atom is contained inside the nucleus, right? So you can say something like the scattering is a result of electrostatic repulsion between alpha particles and nucleus. So the greater the angle of scattering, implies most mass of the atom sits inside the nucleus, because there would be more if the scattering is greater, that would mean there are more protons, because more positive charge in the nucleus would imply that there are more protons in there, and more protons mean more mass. So most of the mass lies inside or is concentrated in the nucleus. An alpha particle, B part, is made up of other particles. One of these particles is a proton. State and explain whether a proton is a fundamental particle. Now, a proton is not a fundamental particle. If you are familiar with the standard model, there is no proton in your standard model, right? There are multiple things. There are quarks, there are leptons, there are bosons as well, right? And so there are multiple quarks, and these combination of quarks makes up a proton, in fact, as well as a neutron. So a proton is made up of 3 quarks. We have 2 up quarks and 1 down quark. So proton is not a fundamental particle because it is made up of 2 up quarks and 1 down quark. Okay, part C, a radioactive source produces a beam of alpha particles in a vacuum. The average current produced by the beam is 6.9 into 10 raised to power minus 9 amperes. Calculate the average number of alpha particles passing a fixed point in the beam in a time of 1 minute. So we have a source and it throws alpha particles. When alpha particles are charged, so basically charges are flowing, that would obviously imply that there is some current, and the value of that current is specified, and we're required to find the average number of alpha particles that will pass a fixed point. You can choose that point in the beam after 1 minute, right? So we know that we can figure out this thing, the total charge, which is given as the product of current and time, right? Now we know that the current is 6.9 into 10 raised to power minus 9 amperes, while the time is specified as 1 minute. That would be 60 seconds. So this would give me a charge of 4.14 into 10 raised to power minus 7 coulombs. So the charge is now specified. We can easily find the number of alpha particles because we also have another equation for charge that says that the total charge is n multiplied by the fundamental charge E, right? The charge of an electron. So this means we know Q is 4.14 into 10 raised to power minus 7 coulombs. N is the number of alpha particles which we want to compute, multiplied by E. E is 1.60 into 10 raised to power minus 19. So this would give me a value for N as 1.29, but there is one factor that you have to input over here, and that is multiplied by 2. Why? Because remember we're talking about alpha particles, right? And for alpha particles, the charge E is basically 2 times E, because it has this is how we can write an alpha particle. It has 4 mass number into number of electrons, right? So there are 2 electrons, so you multiply the fundamental charge of electron by 2. And so you do that, and this gives you 1.29 into 10 raised to power 12 total number of alpha particles. So the answer is 1.29 10 raised to power 12. Finally, part D, the alpha particles in a vacuum enter a uniform electric field. The alpha particles enter the field with their velocity in the same direction as the field. So we can draw something for this. Let's try to picture what's happening. These could be the two plates. Suppose this is positive and this is a negative plate, and so the field lines would be in this direction, right? Coming from positive and entering inside negative. Now suppose I put an alpha particle here, and they have mentioned that its velocity is in the direction of the field, so it will also be in this direction. Okay, now state and explain whether the magnitude of acceleration of alpha particle due to the field decreases, increases, or stays constant as the particle moves throughout the field. Now we know that the force that acts on the particle due to this electric field is given by F equals Q times E, right? The charge times the electric field, which means that the force is in the direction of the electric field, right? Now, as both electric field strength and charge on the alpha particle, they are both constants. We're not varying the electric field, and the charge, we found out, it's just a constant number. That would mean that the electric force is going to be a constant as well, right? And now if electric force is constant, then we know from Newton's second law that net force is always given as m times a, which means that because mass is obviously constant for alpha particles, that should imply acceleration should also remain a constant to make sure that the force F is a constant. So you can answer this problem in your words by saying that since force is equal to, electric force is equal to Q times E, the electric field is a constant, and so is the charge, which would imply that the force is constant. But from second law of Newton, we know F is equal to ma, so if F is constant, that would imply acceleration is also constant.